topic is about grammar. So we'll be seeing grammar today with introduction and its definitions and what are the types of grammar we have. We will see some example how to identify the type of grammar for the given example. Then we will be seeing the derivation forms of the grammar. So before going to the grammar, we should know that when there is a language is there, you need an acceptor, that is a finite automata, to recognize that language. Similarly, you need a generator to generate the grammar for the language. So why do we need a grammar for a language? So with the grammar we can say whether a language is regular or not regular. So here we are going to use a grammar is used to generate the entire string for the given language. So it contains some set of rules which is used for a proper conversion from one state to the other state. So Norman Chomsky, he has given a mathematical model of grammar, so which is for writing the computer level language. First, let us see what is grammar is. A grammar is formally described using four variables: V, T, S, P. So V stands for set of variables or non-terminal symbols. Okay, so it will be usually represented using capital letters. And T will be a set of terminal symbols which will be usually represented as small case letters. And S stands for starting symbol, and P is meant for the production rule, which will be containing both terminal and non-terminal symbols. So what is a production rule? So before going to the other types, so we have to know what is a production rule is. So here the production rule is in form of alpha implies beta. Both alpha and beta will contain terminal and non-terminal or both symbols. Okay, but an alpha implies beta, it must contain at least one non-terminal either in alpha or in beta. So that is the most important part of the definition of grammar. What are the different types of grammar we have? We have type 0 to type 3 grammars. Okay, so we'll see what is type 3 first. So type 3 grammar is called as the most restricted grammar. We have other name for type 3 grammar, that is regular grammar, and the language generated from this grammar is called regular language. So you will be using a finite automata for its automation. And type 2 is, it's less restrictions it has compared to type 3. It is otherwise called context free grammar, and the language generated will be a context free language. We will be using push down automata. Type 1 is going to be context sensitivity grammar. So it's the language generated will be called as context sensitivity language, and you will be using a linear bound automata. And type 0 is an unrestricted grammar. So you don't have any restrictions in the type 0 grammar. So it is called unrestricted grammar or recursively enumerated grammar, and the language generated will be referred as recursive enumerable language. So you will be using a Turing machine for these type of grammars. Let us see one by one what is the rule for that. So how the type 0 grammar is defined, something like that. So in the diagram what I have given here is, you can see the innermost circle is type 3 grammar here. So what it does means is, if a grammar is in type 3, okay, then it can be of type 2, type 1, type 0. But if a grammar is in type 2, it may or may not be in type 3, but it is definitely type 1 and type 0 grammar. So that is the meaning it is given in the diagram. So the innermost circle is type 3. So if any grammar is type 3, then we can simply say that it is type 2, type 1 and type 0. So we'll see what is type 0 algorithm. So type 0 grammar, which is otherwise called recursive grammar or recursive enumerable grammar. So it will be having a form alpha implies beta. So think about it as alpha implies beta here. So here alpha may contain terminal and non-terminal symbols, whereas beta also contains terminal and non-terminal symbols. So what is the difference here is, if you see the third line, alpha belongs to v plus t, either terminal or non-terminal variable, and b, that means one b is compulsory, that is there it must contain at least one non-terminal variable. Then again it can be followed by v plus t the whole star, so which is nothing but you may or may not have terminal and non-terminal variables. So what is the most important rule is alpha should not be empty and alpha should contain at least one non-terminal symbol. So that is the restriction for type 0 grammar. So type 1 grammar, which is otherwise called context sensitivity language or context sensitivity grammar. So we have only one restriction here. First thing is alpha implies beta must be in type 0 grammar, where the length of alpha should be always less than or equal to the length of beta. So if you have a grammar of form, the production rule is of form alpha implies beta, the length of the alpha should be less than or equal to the length of the beta. So that is the only restriction we have for type 1 grammar, so which we call it as context sensitivity grammar. So what is type 2 grammar, which is we call it as context free grammar. So all the production rule must be in the type 1 grammar. Here alpha should contain only one non-terminal variable. It should not have any terminal variable with it or more than one terminal variable. So alpha should have only one non-terminal variable. That is the only constraint we have in type 2, where beta can have n number of terminals and non-terminal variables. So type 3 grammar, which is otherwise called regular grammar, and the language generated using regular grammar is called regular language or type 3 language. So it is the most restricted grammar. Okay, so it is the most restricted grammar because it's in the innermost circle of the diagram. So if a grammar is type 3, then we can say it is also in type 2 and type 1 and type 0. So what is the rule here is, so if the alpha implies beta, so the grammar if it is in the form of alpha implies beta, it should have two special cases. So all the rules must be either left linear or right linear. So what is left linear? You can see V implies Vt, that is if the non-terminal symbol V comes in the right hand side as a leftmost, then it is left linear, and if it comes rightmost in the right hand side part of the alpha implies beta, then it is right linear. So I have given an example here. A implies AB. Here capital A and capital B are non-terminal variables and small letter a is an terminal variable. So you can see the example I given. A implies AB, that is small a and capital B, or then the first expression is an example for right linear because B is in the right side of the X, that is A. Similarly small a. Implies BA. Here B is to the left side of small a, so it is left linear, or A can be of empty. So we will see what is the left linear and right linear. So right linear grammar is said to be right linear if all the productions of the form A implies AXB. Okay, so X is a terminal variable or terminal symbol, and where B is a variable or non-terminal symbol. Okay, so you can see B lies to the right side of the terminal symbol X, hence this form of grammar is called right linear grammar. So vice versa for the left linear grammar, you can see A implies BX. Here B lies left side of the terminal symbol X, hence it is left linear grammar. Now let us see examples to identify the type of grammar for the given form. So let us see the first example. So let me have this form. So we are going to identify the type of the grammar for the given form of the given production rule. So let me assign each rule as one numbers. So 1, 2 and 3 and 4. So we'll have a small note here. So what will be the note here is alpha implies beta. So what are the type 0 is? For 0, what is the condition is, as I said, alpha should not be null. It should have some terminal variables. For type 1 grammar, the length of alpha should be less than or equal to the length of beta. And what is the type 2 grammar is, alpha should contain only non-terminal variables, that is, it should belong to V. Third rule is, for the third grammar, that is the regular language, it should be of either left linear or right linear. So that we can write like this: A implies AB, or A implies BA, or A implies epsilon. So this is the rule we are going to check. So how do we check the type of the grammar? So we will start checking from the type 3 grammar. So we will start with the checking for type 3. Why type 3? If a grammar is type 3, then all other grammars are applicable, because if it is a grammar is a type 3 grammar, if it is a regular grammar, then it is of type 2, type 1 and type 0. So what is the first step we are going to do here is, we will be checking for type 3 grammar. Okay, so what is the thing? It should be of left linear. So first, before going for left linear, it should be of type 2. So what is type 2 here is, alpha should belongs to variable, that is, it should be a non-terminal variables. Right, so first you will be asking what is non-terminal variables. So let us assume, I will give you over here, so V, so which are all capital letters that are going to be non-terminal variables. So here it is going to be S, A, B, and we have capital C and capital D. Similarly, what are the terminal variables we have here? We have small a, and we have C, and you have B also. Okay, so A, C and B. Okay, these are the three variables. So what is the starting symbol? We know its starting symbol is S. Now see all the alpha parts. Alpha parts must contain only the non-terminal variables. Okay, so that will refer it as variables alone. So it should have only variables alone. So you can see in form rule 2 and rule 4, alpha is containing terminal symbols. So it is a violation. Okay, so it is not type 2. If it is not type 2, then it is not going to be in type 3. So the given form is not in type 3 or 2. So we will check for type 1 now. So now we are known that it is not in type of 2 as well as in 3. Now we will check for the type 1 grammar. So what is the type 1 grammar here? So you have to check the length of alpha should be less than or equal to beta. So the length of alpha maximum is 2. You can see all the left hand side is with length 2. All the right hand side is with the length of minimum 2 and maximum 3. So here it is of 1, 2 and 1. Okay, so it is satisfying the condition for type 1 grammar. Hence the given grammar is type 1. That is, what is type 1 is? It is context sensitive grammar. Okay, so the given grammar is a context sensitive grammar. Let us have other examples. Now I have given 3 examples. Let us see the first example. So you can see here we have to check for type 3. So you have to check for type 3 grammar, that is regular grammar. So here alpha is containing only, so alpha contains only variables. Okay, so if you want, you can write what is variable is. So here variable is S and X, and T is nothing but only A, C alone. Okay, so epsilon doesn't have any meaning. So alpha is containing V, so it is in type 2 format, as well as the length of the alpha is always less than or equal to the beta part, okay, less than or equal. So it is also type 2 only. So you have to check for only type 3 now. So we'll check for the type 3. So what is the main rule for type 3 is all the LHS, that is left hand side of alpha implies beta, should contain only one variable or non-terminal. So I'll write it as NT here, non-terminal. Okay, so you can see S and K are non-terminal. So you can see other thing is, the most important is A implies A. What is the third rule is? So we'll check that one. So you can see here, the third rule is it should be of in this form only. It is either left linear or right linear. Okay, otherwise it must be empty. So when I see the first expression, I'll take this. So when you see the first rule, x of xa, I can say it is in some left linear, and x implies ax, it is right linear. X implies a, okay, it is having only one terminal symbol, so it doesn't matter. It belongs to epsilon also, it doesn't matter. But you can see here x tends to a, b, c. Here this is containing more than 3 terminal symbols. It's of string format. So type 3 doesn't support any string format. So hence this is only of type 2, that is only of CFG. Okay, so again it's a context free grammar only. Now we'll go for this one. Again, alpha is having only x and y, one variable, no issues. Then when you say x implies a, x implies ay, and y implies b, everyone is having only one terminal symbols, and you have a right linear equation here. So no issues in any of this format. Hence this is of type 3, that is it's a regular grammar. So this is a regular grammar. So what you are checking for regular grammar is it should not have consecutive terminal symbols like A, B, C. Similarly, it should have either left linear or right linear. Otherwise, it is not a regular grammar. So here it is right linear and all other symbols are having only one terminal symbols. But in the previous example, you can see it is having consecutively 3 terminal symbols. Hence, it is not a type 3 grammar. Now coming to this one here. So this is going to be of next form. What is the thing is? So you can see LHS is containing more than one. LHS of AB implies A, B, B, C, small c. Okay, it is containing more than one variable. Okay, more than one variable. Hence it is not type 3. So hence it is not going to be type 3 because it should be of single variable. So it is not type 3. But you have to check whether it is type 2 or not. It is also not type 2 because alpha should belongs to only one B, that is for type 2. So hence it is also not type 2 equation. Right? The last thing is you have to check for only type 1. So what will be the type 1 is you have to check the length of alpha and beta. So less than or equal to beta. Yes, it is valid. Hence it is CSG, that is context sensitive grammar. So that is the example for. So I given enough example how to identify the type of grammar. So this will be very useful in your GATE coachings and other aptitude exams when you are doing for a basic technical round. Right. Next we will see about derivation forms of the grammar. So how do we do? So what I did in the last step is just we checked the grammar alone. We didn't generate any string for that. Okay, so what is the string generated by the grammar for the given language, or what is the language that is generated for the given grammar? Now let us assume the G1 here. So here we'll take this one, this is variable, this is non-terminal variable, and this is start symbol, and this entire thing is your production rule. Okay, so let us have numbers for this. Okay, so I will write over here. So S implies small a capital A B, so let it be as rule 1 or form 1. Okay, next one is A B, this is of 2, and A implies epsilon, right? Now seeing the production rule, tell me what is the type of grammar we are using here. It is type 1. Okay, it is not type 2 or type 3, because you can see there is a terminal variable in the alpha part, so it is not going to be type 2, hence it is not type 3. So this production rule is of form type 1 grammar. Now what is the kind of question is, find the language that is generated for the given grammar. Now first we'll take the rule number 1 here. So I'm going to form a derivation. So we'll form a derivation here. So S implies A B. So this is the rule. So what I'm going to do here is I'm going to find a replacement rule for A B. I can see an alpha part in the second production rule is of form small a capital A. So instead of small a and capital A, I can replace A B. So let me replace that first. Okay, so I will write in this way. So instead of A B, I'm going to write A capital A B, then another B. So using rule 2. So in this way we try to derive the string that is generated by the grammar. So again I can see, again I have a B is there. Again we may apply the same rule again. How many times you are applying, it's up to you. So I will take again A B. Okay, so these two B's has to be returned. So again these two B's, again using 2. Now I'm going to apply the last rule here. So let me assign this. So I'm going to apply A B using rule 3. So epsilon, anything into epsilon is the same regular expression. So only the string we are going to have is A B. So you can have multiple choice, again and again I can replace A with multiple times. So this A can be of any format. So what is the language that is generated here is, you can have a form of with a single representation. You can have, I will write it down here. So if you take this form, if you substitute epsilon over here, you will have AB. If you substitute epsilon over here, you will have AABB. When you substitute in this, it is going to be A B. Similarly, the next one will be 4 A's and 4 B's, and it goes on. So this is the language generated for the given grammar. So I can write the equation form. You can see it is in the form of consecutive sequence. If you have how many number of A's we are having, the same number of B's we are going to have. So you will write A of n, B of n, where for all n is greater than or equal to 0. So this is the language that is generated for the given grammar G1. We'll have another example. Now same thing. So here we know what is V. So V is going to be S, A and B. And what is T is going to be is, T is going to be small a and small b. And your sorting symbol is S, and your production rule is going to be S implies AB and A implies small a, capital B implies small b. So this is the rule. Now we are going to find the language that is generated for the given equation. Fine. So we will do one thing. So first step, I'll take first iteration. So S is equal to AB. So I will apply A alone first. So we'll put a number for this. So let it be as 1. Okay. And this will be of 2. And this will be of 3. Okay. So this is by rule number 1. Again, B is going to be replaced with third rule. So it is going to be AB. Now I can have another way of writing. So let us assume, okay, I have another way of writing over here. So I will be writing AB first. Then instead of, okay, it is of form AB only. There is no other way I can write it here. So let me do some B substitution first here. So capital A, small b, so this is of rule 3 and this is of rule 2. I don't know. So I am substituting rule 3, then again I am substituting rule 2 here. So it's going to be AB alone. So the language generated for the given grammar is going to be AB. Okay, it's just AB. No other thing, no other things can be generated. So that's the language it is generated by the given grammar. Right, we will see the example for the next one. So in previous example we have seen a series, and second example we have seen only one string is generated by the entire grammar. Now if you have multiple possibilities, so how do you write it? So we'll have an example over here. So let me write. So what is B is going to be here is S, A and B, and your T is going to be small a and small b. Your starting symbol is going to be S, and your production rule is going to be S implies AB. So let me take it as 1. Similarly, I have A implies A, capital A. Let me take it as 2. Similarly, A implies A. I will take it as 3, because it's A can be derived to either small a or only small a alone. So I have divided into two rules and I have written here. Similarly, capital B can be given small b and capital B. I will take it as 4, rule number 4, and only small b can be derived. I will take this as rule number 5. Now this is the production rule for the given grammar. Now we will start from here. So I will do with the first substitution. S implies AB. Now I have multiple choice. For A, either A can be substituted or B can be substituted. So let us start from the left side of the right hand side. So from left to right we will start doing it. So for A I can have two choices. Either I can use the equation 2 or equation 3. So let us use equation 3 for the first time. So if I am using AB, then again AB. So this is of using 3 and this is of using 5. So I just used the rule 3 and 5 and I found one. Is the only sequence? No, I have multiple choice again. So let us have the second way of writing it. So AB. So by rule 2 I am going to apply, instead of capital A I am going to substitute small a and capital AB. So this is by rule 2. Okay. So now rule 2 is there. Now again I can substitute, instead of B I can substitute rule 4 also. So if you write rule 4, so here I am going to substitute for B here. So it's going to be B capital B. So this is of rule number 4. Then finally, instead of capital A and capital B, small a and small b can be done. So you will have AA, BB. So this is of rule with 3 and 5. You can see again I have another possibility is written over here. Let me have another possibility. What can be the other strings that can be generated? Okay, I have AB. So instead of A, I'm going to substitute AB. Now instead of A alone, I'm just substituting A. So you have AA, B. Again, instead of B, only B is alone substituted. So you have AA, B over here. So each and every time I'm getting a different symbol. Let me have one more example. Okay, so S tends to AB. Now I'm going to substitute for B alone. So I will have A, B, B, B. Okay, Again for B alone, if I substitute, then again I have A, B, B. Now what I'm trying to say here is I am not able to find what is the format over here, but we can write the equation. So the language for the given grammar, it is generated in the form of AB. Okay, so again here 1A, 1B, you can see here 2A, 2B, and so you will write it as A square, B square. Then for this it is A square and B, so you can write A square B. Here single A, two B's, so you can write single A B square, and it goes on. So how do we formulate this? So we will have A to the power of M, B to the power of N. Why different powers? Because we are having different powers in different string here. You can see here it is having A square, B is having different power. Here A is having one power, B is having two power. So both are not having the same variable here. So for all M comma N is greater than or equal to 0. So this is the language that is generated for the given grammar. Okay, so I have given you 3 examples. First example, I have given you a series formation. Second example, I have given you an exact string formation. And third example, it's a unpredictable series format. So that is a given. Next we'll see another example. So here the grammar is given over here. So you know this is P, this is T, and this is V. We have only one variable here. So we'll stay with the first step. So we'll have this equation as number 1 and this is equation number 2. So let me use the first equation AS B over here. Now I am going to substitute, instead of S I am going to substitute AB over here. So if I substitute AB over here, what happens is it's going to be AB B. AB B. So this is of rule number 2. It's because of rule number 2. So I can write in another way also. Okay, AS B, again using rule number 1, I can substitute AS B, again B, instead of S, using rule 1 I have done that. Okay, now instead of S I will substitute AB alone. So you will have A B B B. So this is using rule 2. So you can see here, if I have A, the same number of B's here. If I have same number of 3 A's here, then you have same number of B's here. So you can write the formula in such a way that the string can be derived in A into A n minus 1 S of B of n minus 1 into B. Okay, so this is just, I am writing, if it is n terms, one term is done, then we have 2 terms, A into A square, A into A1. So this is how it is written here. So I can formulate this equation simply A of n, B of n. So the language generated for the given grammar is A of n, B of n, and for all n is greater than or equal to 0. So this is the language that is generated for the given grammar. Let us see another example. So this is going to be grammar G5. So you can see here I have B, T, S, and I have a P. So whenever you have a transition to the self state, then it is going to be a only production which has no terminals on the right hand side. So you are not having any terminal symbols on the right hand side, so hence we cannot generate any string from the production rule. Okay, hence you don't have any language for the given grammar. So the reason is, what is the reason? We have no terminals symbol in right hand side of the production rule, right hand side of P. Okay, so hence we don't have, our language generated for the given G5 grammar will be of empty. So this is also another example. So let us see the next example. So here we are going to have this formula. So here my production rule P is going to be S implies ACA and C implies ACA or C implies B. So you will have it as rule number 1, rule number 2 and rule number 3. So we have to find the series. I hope that we have multiple options here. So let me start with the first option. So S implies ACA. So now I'm going to just substitute for C using rule number 3. So you will get ABA. So this is because of rule number 3. So I can do another option. So we'll have another possibility. Instead of C, I am going to substitute CAC. Okay. So CAC. Now instead of C, I'm going to use rule number 2 here. So AACAA. Now using rule number 2 here. Okay. Now I'm going to use rule 3 here. So AABAA. So now this is going to be used rule number 3. So what do you find over here? You can see here, if the left side of B, how many A's are there? The same thing is for right side of B also. So it is nothing but A of N B into A of N. So the language generated for the given grammar is of form A of N into B into A of N for all N is greater than or equal to 0. So this is the, okay, it's because you have single variable here, so it's going to be of 1. Okay, it's a 1. So that is the language that is generated for the given grammar. Let us see another example. So here the one and only production rule is going to be S implies 0S1 and S implies epsilon. Okay, so we'll have this rule as rule number 1 and this is rule number 2. Same thing. So let me start with S of 0 of S1. So when I substitute epsilon for S, it will be 0, 1. Okay, using rule 2, 0, 1. So this is first test case. My second option is S is equal to 0S1. So substitute 0S1 again for this. So you will have 0, 0, S1, 1. Now instead of 1, I can substitute epsilon. So it's going to be 0, 0, 1, 1. To make sure whether it is having even number of zeros and even number of ones, let me try the next example also, next option also. So S is equal to 0S1. So now instead of S, I'm going to substitute again. So 0, 0, S1, 1. Again, instead of S, again I can substitute the same equation. So 0, 0, 0, S1, 1, 1. Finally, we'll apply the rule 2 here. So you'll have 3 zeros and 3 ones. So you can see equal number of zeros and equal number of 1 is there. So the language generated for the given grammar is ON, 1N, and for all N is greater than or equal to 0. So when this N term will be greater than or equal to 0 or greater than or equal to 1. When your production rule is having epsilon for any part of the question, then you can use 0 here. If epsilon is not there, then you have to use greater than or equal to 1. So how do it happen? See the previous example. In the previous example, I don't have any epsilon termination. Hence, my N of N should be always greater than or equal to 1. Whereas here, you can see it is having a transition to epsilon. Hence, you may have 0 possibility also. So, I am giving us N is greater than or equal to 0. So that's all for today's topic. So we have seen what is grammar, the definition of grammar, what are the types of grammar, how to identify a type of grammar for the given example. Then we have seen the derivation form of the grammar too. So thank you.